Thank you for listening to our lectures today, and thank you to MinSouth for hosting this event. My name is Martha Needs, and I'm a geotechnical engineer with Knight Piezald Consulting in London, where I have specialised in tailings for the last 3.5 years. This lecture is titled Reducing the Risk of Legacy Tailings Facilities. During this lecture, we will have a brief introduction to tailings and look at identifying the problem with legacy facilities. Second, we will review the key risks for legacy facilities seen at mining projects globally. Lastly, I will produce a remediation framework based on this review and show you how we adopted this framework for a case study in Central Asia. But first, what are tailings and why are legacy facilities such a critical obstacle for the mining industry? As many of you know, tailings are a waste product from the mining process, primarily made up of sandy, silty material and process water, and often in conventional methods it forms a slurry consistency. Tailings material parameters can vary greatly depending on the water content, resource type, native rock geology, and processing methods. Tailings are stored using several methodologies, including paste backfilling underground, disposal into retired in-pits, and pumped to be retained behind engineered embankments. Engineered embankments present as the highest stability risk when constructed and managed inappropriately. Closure phase of a tailings storage facility entails the decommissioning of tailings dams when production has ceased, with the objective of achieving long-term physical, chemical, ecological, and social stability with a sustainable and environmentally appropriate after-use. Legacy facilities are an informal title given to older facilities that are typically closed or inactive, with problems left for future generations to resolve. Standards are mandatory and are often seen as part of the law in particular regions or countries. Breaking a standard could result in fines, penalties, or suspension of works. In comparison, guidelines should be viewed as best practices and cover a range of critical aspects such as required factors of safety, the stability modelling, and consequence assessments. Some international guidelines often used for tailings best practice are shown here. In particular, the CDA, ICOLD, ICMM offer several technical bulletins that should be carefully considered at all stages of TSF life. Historically, only 20% of TSF failures have occurred during the closure phase, so why should we care about these facilities? Well, when reviewing the data on active and inactive tailings facility failures from resources such as ICOLD, an interesting trend is noted. Active facility failures begin to reduce in frequency starting from the period of 1996 to 2007, which is when several key bulletins on tailings best practice were issued, including the CDA guidelines. This could be interpreted as evidence of better tailings management and design as a consequence of the advancement in best practice guidance. We can expect that as further advancements are made, the frequency of failures in active facilities will hopefully decrease. Inactive facility failures, however, do not show this trend, as they were designed and built to outdated standards, and as monitoring activities on closed facilities reduced significantly, in some cases not being monitored at all. It's no surprise that we don't see a reduction in failure frequency. Unless the industry takes seriously the problems posed by legacy tailings facilities, we can expect this trend to continue. There are many reasons why a facility can fail, with the predominant causes including slope instability, overtopping, and seismic deformation. When a legacy facility fails, what can it look like? An example of this is the very tragic and catastrophic failure of the Feijão iron ore TSF in Brumadinho, Brazil. Midday on January 25, 2019, the closed facility failed due to liquefaction. 270 people lost their lives, including those working at the mine and the population living downstream. This event has put the risk of tailings facilities in the spotlight and has been the catalyst for the 2019 issue of the Global Industry Standard on Tailings Management. We will now look at the key risk factors identified for legacy facilities. As noted in our project experience globally from sites in Eastern Europe, Central Asia, South America, and more. The data used to identify global trends in construction methods and TSF activity has been sourced from the Global Tailings Portal by Grid Arendal in collaboration with the Investor Mining and Tailings Safety Initiative. A conventional tailings embankment often uses one or more of these three construction methodologies. Upstream construction uses the least embankment material and therefore has the lowest implied cost, but is also viewed as the least stable. When looking at the global data of disclosed TSFs, upstream facilities make up 54% of all tailings storage facilities. However, when we split this data between active and inactive facilities, we see a 15% increase from upstream construction in inactive facilities compared to the active. Upstream facilities are very sensitive to any increase in water level or strength loss of the tailings, which can be seen when the tailings are undrained or liquefied. During closure, repeated wet-dry cycles, where each wetting cycle is slow to dry, could be building an increasing level of total saturation, potentially forming an increased liquefaction risk. It should be noted that upstream construction can be fit for purpose for many TSFs, and upstream construction dominates in southern Africa, where there is a semi-arid climate and low seismicity. Retaining embankments are typically made of zoned areas of local available materials. The hydraulic relationships between these materials are key in reducing the pore pressures within the embankment, with low permeability material acting as a barrier and the drainage material allowing seepage through a controlled pathway. What we often see in legacy facilities is a lack of this zonation. These raises often consist of bulk soil fill and don't have a barrier or controlled pathway for seepage. This often leads to seepage coming out in the middle of the embankment. Understanding the foundation is also very key to understanding the risk, and unfortunately for many legacy facilities there has been very limited ground investigation works. This often means that they have been built on weak layers such as clay, which could potentially cause a foundation failure. Closure should be considered at the start of the project, but it's often an afterthought and seen as a problem for future generations. The appropriate closure design and monitoring schedule, considering best available techniques not entailing excessive cost, also known as backneck, is key for a successful closure. There is often no end date to the passive closure phase. International guidance such as the CDA recommend that flood and earthquake return periods should be selected based on the dam classification. We see in many tailings facilities that the return periods used for design are significantly lower than the dam classification they've been assigned. This means that the water management infrastructure and the seismic stability may not meet international guidance. So, the proposed remediation framework to reduce the risk of legacy facilities is based on the risks I've just discussed and follows the principles of BATNEC and the European Commission of 2012, but with a focus on legacy facilities. The proposed remediation framework adopts 7 stages. Stage 1 is for assessing the risk, where an independent third-party audit is completed on the facility to review all relevant and available documentation, visit site, and provide recommendations for improvement. Stage 2 is for filling in the knowledge gaps that were identified in Stage 1. This could include ground investigation with in situ and laboratory testing, an environmental impact assessment to determine any at-risk species, habitats, or protected areas, a dam breach assessment to determine the breach inundation zone, and a hydrological assessment and seismic assessment. Stage 3 is for updating the stability models based on any of the findings and updated material parameters identified in Stage 2. Stage 4 comprises an options study to assess the available remediation options for any stability, environmental, and social risks. Local standards should also be considered. Stage 5 is for the feasibility and detailed design, which should be conducted by an appropriately qualified independent third-party engineer. The design may require sign-off by a local design institution in some regions. It's imperative that the design should consider BATNEC principles, passive options, and local capability. Stage 6 is the execution of the remediation measures. This can be performed by a specialist or appropriately qualified local contractor. Quality control should be completed by a third-party engineer. The final stage is Stage 7, which includes monitoring and inspection that will continue throughout passive closure. Monitoring should be performed regularly and, if possible, remotely with an online dashboard. During inspections, confirmations should be made to assess if the remediation measures are working as intended. The case study I'd like to highlight today is based on a project in Central Asia. I've been coordinating our work there since 2019. We have been completing audits at this site for the last 3 years, and we were commissioned in 2021 to complete a remediation study on one of the TSFs. The copper mine TSF started operating in 1980 and is now entering the active closure phase. The facility used the upstream construction method with embankment made up of one bulk soil fill. Here you can see myself on site during last year's audit. So using our remediation framework, as part of stage 1, we completed annual audits of the facility. The audits identified that there was very limited documentation on ground conditions, production history, and material parameters, and the stability analysis indicated factors of safety were below CDA guidelines due to a weak clay layer in the foundation. There was very minimal monitoring and instrumentation on the site, and a lot of erosion was present, as you can see in the August 2019 photo. As a result of the recommendations made in 2019, in 2020 there were more monitoring instruments installed and much of the erosion had been remediated. Further recommendations had also been for the completion of in-situ testing and a dam break assessment. As part of stage 2, the recommendations were completed. The cone penetration tests were performed to provide us updated material parameters for the tailings, embankment and foundation. We also completed a detailed dam break assessment on the site, and as a result recommended the increase of the dam classification to extreme, the highest classification according to the CDA guidelines. In stage 3, we updated the stability models using the updated material strengths. This gave us a more accurate indication of the stability of the TSF, which was still below CDA guideline factors of safety. During the stage 4 options assessment, we looked at several remediation methods, including buttressing the embankment, shown in purple on the model, reducing the pond on the TSF, and removing tailings. After a detailed sensitivity analysis, it was decided that reducing water on the TSF was the critical factor in achieving successful remediation, and several methods of completing this will be used as part of the design, including pumping the pond away from the facility and installing further drains and pumps to reduce the water in the tailings and the embankment. A portion of the stage 6 execution has been completed, with a smaller embankment receiving a supporting buttress in 2021. The remaining construction is due to start after issue of the detailed design, which can be expected in Q2 of 2023. Monitoring and inspection for stage 7 has already been procured, with vibrating workpiece monitors set to be installed after the snow melt in April. Regular audits are being completed and daily inspections have been established. In close, legacy facilities have been viewed to be just waiting to fail, and I propose that if the remediation framework set out in this presentation is carefully applied, this risk can be reduced. It's surprising how many facilities are out there, and many owners don't even know they exist due to lost documentation. When taking on a historical project, it's key to thoroughly check if there are any legacy facilities that may have been left after operation. And as always, reduce the water. Thank you so much for watching this presentation. I'm happy to take any questions.